When most people picture modern AI, they imagine a single, all-powerful brain, a monolithic entity absorbing massive amounts of data and spitting out answers. At its baseline today, an AI agent is a large language model equipped with three things: tools, memory, and the agency to execute tasks. It parses a prompt, it calls APIs, it writes code, and moves data to reach goals. To test the limits of this setup, consider a complex enterprise workflow. Take an automated market research pipeline. This process requires scraping the web, analyzing the data, validating the numbers, and formatting a final report. Assigning that entire pipeline to one agent is the equivalent of demanding a single human employee act as the lead researcher, data analyst, fact-checker, and graphic designer all at the exact same time. This creates what we call context bloat. The agent's memory window becomes oversaturated with conflicting instructions, competing priorities, and dense intermediate data. This diagram shows what happens when that single central node takes on too many simultaneous operations. The task complexity creates a fragile state, where the language model can no longer reliably parse its own operational steps, and the logic breaks down. Errors immediately begin compounding. One minor hallucination during the initial web scrape silently corrupts the analysis, which then corrupts the final report. While a single agent setup looks impressive in a controlled social media demo, serious engineering teams do not rely on it for actual enterprise workflows. Achieving reliability in production requires moving away from the monolithic model. Engineers must shift to distributed, multi-agent topologies. Moving to a distributed system enables three architectural advantages: deep task specialization, true system parallelization, and infinite scalability. By isolating narrow tasks and applying highly specific system prompts, individual agents achieve significantly higher accuracy than a generalist model trying to process every instruction at once. Those specialized agents can then execute their independent tasks concurrently. Running parallel operations drastically reduces the total time to completion for complex workflows. As the workload grows, this distributed architecture allows engineers to add new capabilities and deploy new agents without having to rewrite the underlying system from scratch. To deploy these distributed systems, developers rely on distinct design patterns. The most ubiquitous pattern in production today is the orchestrator-worker topology. This graph displays the structural hierarchy of that pattern. We have a large central orchestrator node managing several smaller worker nodes. The strict limitation of this central orchestrator is that it executes no actual labor itself. Its only job is to plan the overall goal, route the specific tasks to the workers, and synthesize the final output. The worker nodes execute the narrow tasks simultaneously. Once finished, they return clean, processed data back to the center. The second major pattern is the sequential pipeline, designed specifically for rigid, highly predictable processes. This diagram represents a directed acyclic graph, or DAG, the logic flow driving the pipeline. The key here is that data moves strictly forward and cannot move backward. This strict linear sequence makes it ideal for enterprise applications like document processing or automated data transformation workflows, where the required steps rarely deviate. Applying these topologies provides the structural predictability required to manage multi-step agentic workflows. When a workflow exceeds the management capacity of a single orchestrator, the architecture must expand into a hierarchical multi-agent model. This chart shows how a hierarchical system mirrors a massive enterprise organizational structure. A master node sits at the top, managing department-level orchestrators for macro functions like inventory or logistics. Those mid-level nodes then manage their own dedicated pools of workers. The fourth and most complex pattern is the decentralized peer-to-peer network. This visualization illustrates a peer-to-peer system, defined by its deliberate absence of a central management node. Because it lacks top-down control, this topology is reserved for highly specific applications: multi-agent simulations, competitive modeling, and scenarios requiring emergent decision-making. The critical drawback is that these networks are inherently harder to debug and control, making them rare in standard, predictable production environments. True production systems rarely rely on just one of these patterns. Engineers combine them, often nesting rigid sequential pipelines inside the worker nodes of a larger orchestrator setup. These topologies provide the necessary blueprint for delegation. But the entire network instantly collapses without robust underlying infrastructure to manage memory and state. Designing agent connections on a whiteboard represents the happy path. Assuming the system will naturally run without errors is a massive engineering fallacy. The most critical and frequently ignored component of multi-agent engineering is establishing an explicit memory architecture and state management system. This diagram outlines the 3 distinct memory tiers required for a production system to function without data collision. Tier 1 is short-term in-context memory. This must remain strictly private to the specific agent executing a current task, preventing it from getting distracted by the rest of the network. Tier 2 is long-term vector storage. This is utilized across the entire network for semantic retrieval of historical data and standard operating procedures. Tier 3 is shared external state architecture, using tools like Redis or Postgres. Here, agents constantly read and write the global status of the overall workflow to keep everything synchronized. Even with perfect memory management, dynamic failure in distributed systems is inevitable. A single malformed JSON output or a mid-pipeline API timeout will instantly cascade, breaking every downstream agent relying on that data. To survive this, engineers build strict architectural guardrails. This includes explicit retry logic, implementing fallback behaviors, and human-in-the-loop checkpoints for high-stakes decisions. Deploying a reliable multi-agent system requires defensive software engineering and a proactive strategy for managing failure states. In distributed systems, observability is a functional requirement that must be implemented before writing the first line of agentic code. This dual-pane diagram demonstrates why. On the left, we see a highly tangled, failing 8-node network emitting errors. On the right, a clean, minimal 2-node setup smoothly transferring data. Proper observability tools map the graph in real time, logging exactly what context an agent received, what tools it called, and what it produced. Without that granular tracing, debugging a distributed cascade failure in production is practically impossible. The most common mistake teams make is jumping straight into a code editor before decomposing task boundaries and handoffs on paper. This leads to complexity bloat, designing elaborate 8-agent networks to solve problems that 2 agents could handle perfectly well. Every additional agent introduces coordination overhead, increases latency, and creates a new potential point of failure. The simplest multi-agent system that reliably solves the problem will always outperform an elegant, over-engineered monolith that fails to ship.